The whole point of this video is just to prove Clairaut's theorem. So this is a very famous theorem from multivariable calculus. And what it ultimately allows us to do is say if our function f, which we are differentiating, is nice enough, then when you look at mixed second order partial derivatives, the order that you compute them doesn't matter. In other words, f sub xy, which means we differentiated first with respect to x and then y, is equal to f sub yx, differentiating first with respect to y and then x. What we need our function to satisfy is that it is class C2 on its domain. C2 means that its partial derivatives up to second order, so first and second partial derivatives, exist and are continuous. In other words, when you compute these kinds of expressions for your function, they're pretty nice functions in their own right. I didn't say it yet, but f is a scalar-valued function of n variables. We will imagine it has some nice open domain A, which is a subset of Rn. And what we are just going to do in this video is establish this equality. I want to say that, I don't know, maybe the internet has changed since the first time I Googled Clairaut's theorem. There are a lot of proofs on the internet that I don't think are very well done. In particular, I will actually show you the moment that I think is iffy, but I'm going to give you a very rigorous, very correct proof of this. If you see a different proof somewhere and you think, hey, that's easier, it might be possible that it's essentially relying on this result. So I caution you to just be aware that there may be proofs out there that sort of oversimplify the theory. Okay, I actually think that's where we're going to start. So what I will do in just a moment is begin a proof, or I'll begin a computation that doesn't lead to the proof. I'll show you what people sometimes try to do with this computation, but does lead to something useful that we will need for the proof. So let's start there. Real quick before we move on, I forgot to discuss the start of this proof. The proof that we are going to write down ultimately will work for a function of n variables. If we are looking at changing the order that we differentiate with respect to just two of the n variables, then all of the other variables are going to be fixed. So we would only perturb inputs in two senses of direction and everything else would be fixed. So what we will do for simplicity is imagine that we are just working with a function of x and y. And again, the proof is completely valid, but if you wanted to try to take what we do and extend it to the setting of having a domain, which is a subset of Rn, basically you'll have like more dots in your inputs. Okay, but the theme, the way that we do the proof will carry over. We want to show that f sub xy at any point a, b in the domain is equal to f sub yx. What I'm going to do now is just a manual computation of what differentiating df dx with respect to y looks like. I think once we get in the habit of taking derivatives, we just look at a function, differentiate with respect to x and y, and we kind of forget that in the background is a sequence of iterated limits. So let me write down what those limits look like. We're going to take the function that we produced by differentiating f with respect to x, and we're going to take that function and differentiate it with respect to y. So differentiating with respect to y means we did a limit, and this is what the limit would look like. It would be the limit as some perturbation term k goes to 0. I want to take f sub x, df dx, and freeze it at AB, and then imagine just perturbing it in the y-coordinate only. So the correct numerator for this difference quotient will look like df dx at A, B plus this little perturbation, so B plus K, minus how this function behaved at the point AB. That over K. Okay, it's tempting here to think of K as positive, and later we'll actually have a picture where K will look positive, but it doesn't have to be. Okay, that is the difference quotient that would produce f sub xy, but each of these terms in the numerator is itself a derivative. So now I would like to take this numerator and go to the next layer, and let's say how each of these terms were computed with respect to their own limiting actions. So let me take this 1 over k and kind of pull it out front. We'll have the limit as k goes to 0 of 1 over k. 1 over k times this expression minus that expression. I am going to compute both of these derivatives with respect to x inside of a single limit. You could do it as two and then just put them together. So let's say that each of these is the limit. Now we're going to take f and perturb it in the x-coordinate. So it's like to get each of these, it's its own limit. So this will be the limit as h goes to 0 of here. This was f of a plus h, b plus k. So that's taking this input and perturbing in the x-coordinate only, freezing the y-coordinate as it's written in this first term in the numerator. So that minus where we started. So f at a b plus k. All over h. Okay, let me give you a moment. Write the other term. All right, hopefully this is what you write down. We want the difference quotient that produces this expression from the numerator. That's going to be, I'm going to do it right here, but I'll try to put them all together in just a moment. So it's going to be same limiting action. So let me just say from here, we're going to subtract off f. We start at ab, but we perturb a little bit by a factor of h in the x-coordinate. So a plus h comma b minus f of ab divided by h. Okay, so all of this, when we compute that limit as h goes to 0, it will produce this x partial derivative. Likewise, this one will produce this x partial derivative. I'm like, I should have written it all in one line. Let me try to do that now. So I'll write this as condensed as I can. This will be the limit as k goes to 0. I'm going to leave the 1 over k out here, times the limit as h goes to 0. And I'm actually going to pull 1 over h out front too. And have this times this minus this. So f of a plus h, b plus k, minus f a b plus k, minus, careful with the negative here, minus f of a plus h, b minus minus, so plus f of ab. I think I have more parentheses than I need, but here we go. This limit exists. Everything here exists because we know that all the second partial derivatives of f exist and actually are continuous. Here's where I would stop this computation, though, and get a little bit concerned. And that is, and this is what I see on the internet, is sometimes people kind of rearrange terms and say, like, okay, bring the k in. So we could do this one minus this one. So this minus that, pair these up. Let me highlight that. Take this term minus that term. This is comparing how f changed after a little step in the y-coordinate. Bring this 1 over k in, that's fine. So that we'd have this minus that divided by k. That's all fine. You can bring the k in, you can repartner these up. In fact, we will do that in the proof. But what I don't like is that explanations will then say, and then switch the order of the limits. So, bring the k in, rearrange terms, do this, and then this. So that you take the limit as k goes to 0 first, and then as h goes to 0. And if that's fine, yes, you would actually, after rearranging terms, produce the derivative of df dy with respect to x. So you would switch the order of the mixed second partial derivative there. This, though, I think this needs to be done very carefully. Limiting actions do not necessarily commute. So this is two iterated limits. You cannot freely interchange limiting operations in mathematics. It does actually end up being valid here, but I only know that because I know that Clairaut's theorem is true. So, I would say, okay, well, since the mixed partials are going to be the same, yes, it works. But that's me already knowing that Clairaut's theorem is valid. I think if you're going to do this interchange of limits, it really needs a careful justification. And I don't usually see that whenever I've seen this proof on, websites. So I would caution you to challenge any proof that interchanges limits ever anywhere in math without saying why they can do that. However, that doesn't mean that this whole demonstration was a waste of time, because we are going to take these four f expressions and work with it. So this is very much the computation that we will need to kind of experiment with in order to get to the actual proof. I have a little warm-up activity for us to do before we do that. So make sure you have this written down. And one thing I would like for you to do, if you want to pause and work through that, is imagine looking just at the inputs. So take these four inputs, a plus hb plus k, ab plus k, a plus hb, ab, these four places where we are evaluating f, and actually diagram them. So imagine, if you were plotting these as points, what would that form? So try to give some visualization for where these four inputs live. Okay, this might seem like it came out of thin air, but we will see this kind of computation a few times in the proof. So I thought it would be nice to go through the mechanics of how this kind of computation works now, instead of in the middle of the proof while we're thinking about other things. So this is just a demonstration with three differentiable scalar-valued functions. I didn't write down very fancy hypotheses, but the idea is, say this function g is a function from r to r, which is differentiable. H and c are scalar-valued functions of two variables. In analysis, you often see a difference of outputs. So here, in this first example, we are looking at the difference between g at 2 points. And it might make you think like h is very small, maybe a plus h is moving to a, but let's imagine that these are static points. So I don't want to think of this as sliding around. This is g being evaluated at two discrete points. This is a difference of outputs. It's a change in g. There is a way to pass from a change in function values to a rate of change. Those are two different ideas, but they're related. So it's like, I want to take these function differences and replace them, rewrite them with some kind of rate of change. So passing from a change to a rate of change. There's a way to do this. And that is to recognize that this looks kind of like the numerator in a difference quotient. Again, I'm not going to take a limit or anything like that, but let me take this difference in outputs and divide it by what I would like to see were I writing down a difference quotient, and that is the difference in the inputs. So it's like difference in outputs divided by difference in inputs. Here, that would look like a plus h minus a. But as we know, you can't just divide. We need to balance that out. Okay, so now all I've done is take this expression that we started with, g at a plus h minus g at a, and I've multiplied it by a very fancy version of the number 1, so h divided by h. What we have here is change in outputs divided by change in inputs. This looks like a difference quotient. There's no limit happening here, though. H is a fixed number greater than 0. If you were to graph g, in fact, let me imagine doing that. Perhaps this is the point a plus h, g at a plus h. Sorry, writing all the way to the end. And this is the point a, g of a. Physically, what is this ratio computing? For the scalar value function of one variable, you could call it rise over run. It's a slope, and it's the slope of the secant line connecting these 2 points. There is a very famous theorem from Real Analysis 1 allowing us to pass from the secant line and the secant slope to a tangent line, so a tangent slope. In other words, I know that somewhere between these 2 points, I didn't have to draw this carefully. I knew it was going to happen. Somewhere between these 2 points, there's a place on the graph of this function where, let's say it's about here. I'm going to have to graph somewhat carefully, but it's my artistic limitations. About here, the tangent slope is parallel to the secant slope. And that theorem is the mean value theorem. So the slope of this line is this ratio. We can now say that at some point, typically it's called C in the language. So C, G of C. At some point, C between A and A plus H, G prime at C, the slope of this tangent line, will be the same. We know it happens at least once. So what we're going to do is take this secant slope and replace it with g prime at c times h. Always be careful when you're using this kind of theorem to state like what this is. So I would write for some c between a and a plus h. Not for all c. You don't get to choose the c. You just know that there is some c between these two inputs where g prime at that particular value, sorry, marker down, g prime at that particular value would be equal to this ratio, and then the h is just going to carry over. Okay, for the second one, we are looking at a function of two variables, but decide if we can do something similar. Let me give you just a moment to look at h and c before I come back and quickly run through how we will take these differences in outputs and convert them into expressions involving a rate of change. First, my apologies for overusing the letter h. So I had the function was named little h, and then the input is a plus h. It's a different h. So I've changed the name of this function to capital H. I hope that's okay. Just like in the first example, we have a difference in outputs for the function capital H. So it's a change in function values. We want to replace it with some kind of rate of change. So going from a change to a rate of change. If you look at what's being compared here, it's not H at two totally different inputs. The second input is fixed at B. So we could think of this difference in capital H expressions as happening in the plane y equals b. It's really a problem with one variable, just the first one. Y is fixed at b, the computation is happening in the plane y equals b. That should make you think any kind of rate of change is with respect to the x coordinate only, and that's really the key here. Now that we've identified that, let me just write it straight down. I'm not going to sketch a picture. Just like in the first example, we're going to take this and divide it by the change in inputs. So change in outputs divided by change in inputs. This time, if you wanted to graph capital H as a function of x and y, in general, it would be a surface, some kind of wavy piece of paper in three-dimensional space. But when we chop into it with the plane y equals b, we're tracing out a curve, just like the curve that I've erased. So again, this is really a computation with respect to just one variable only. We have change in outputs where the only perturbation is happening in the x coordinate divided by change in inputs. I need to multiply this by h. Sorry, I did that way too close. Okay, there we go. And, times h, this is going to hang out. What's happening here is, again, if we freeze our computation is happening in the plane y equals b, we're going to have 2 points connected by a secant line. This difference quotient, where all the action is happening just with respect to the x coordinate, is going to compute the slope of that secant line in the plane y equals b. And there's going to be some input whose x coordinate is between a and a plus h, where the slope of that secant line is equal to the rate of change of h along that curve. Well, that's happening with only respect to the x variable. All I'm trying to say is that this is going to be d capital H dx at some, let me write down c and we'll fix that, comma b. The y coordinate here is frozen at b, and then times this h. Exact same as here, it's just our notion of prime becomes differentiation with respect to x because computation is happening in that direction. I mentioned earlier that this phrase is often left out. In fact, I just left it out. And also, you have to be really careful. We call these points C all the time, but sometimes I've seen students use C in one place and C in another place, and then they think maybe it's the same C. They kind of lose track of the distinctions between C's. We are going to do this computation numerous times in the proof. So I will annotate, like the first time we do it, I'll call it C1. The second time I might call it C2, or I'll call it D. So I'll be careful how we describe this kind of point where the tangency is mirroring the secant slopiness. So when I start dropping subscripts onto things, that's why we're doing that. So to be really complete, let me say for some C2 between A and A plus H. Okay, y is fixed at b. C, our final function, is very similar, just different coordinates. So let me give you a moment, see if you can write down the final expression kind of this form. Okay, I don't want to say too much because we need to get going with the proof. So hopefully you understood that the thing to do here is recognize that x is frozen at a. All the action is happening with respect to the y coordinate only. Let's take this difference in outputs, divide it by a difference in the input where the action is happening. That's division by k, so we need to bring that back. And then once we realize this is a difference quotient in the x equals a plane, it's a secant slope, we can pass to a tangent slope in that plane. That will give us C, that's my attempt at it, sub y. So the derivative of this function with respect to y, x is frozen at a, y will be, typically I call it d when it's in this coordinate. So we'll have c's and we'll have d's. And then here we'll say for some d between b and b plus k. Okay. I think we will see this kind of conversion from a difference in outputs to a rate of change expression maybe 4 times in the proof. The first time I'll probably really talk through it and we might move a little bit faster the second, third, and fourth times. We will stick with this convention that when it's in the x coordinate, we'll use c's. When it's in the y coordinate, we'll use d's. And notice I said between a and a plus h. I didn't really order these. I could have written them as an interval. And that's because h and k don't necessarily have to be positive. So it's tempting to think of them as positive, but we'll say between just to cover the case that actually a plus h is to the left of a. Earlier, when we were doing that iterated limit computation to get the mixed partial derivative with respect to x and then y, we arrived at f evaluated on 4 different inputs. I challenged you to try to graph what those inputs would look like, what kind of shape they would produce, and hopefully you came up with a rectangle. So here we have a, b, and then if I imagine, although it's not required, that h is positive, a plus hb would just shift me to the right. And then again, if we imagine that k is positive, although it doesn't have to be, a plus h, b plus k would shift up. And then the other one was a, b plus k. So we get the 4 vertices of a rectangle like this. H and k don't have to be positive. And what I was trying to emphasize here with this very rectangular shape is they don't have to be the same either. So I can just imagine them producing any 4 vertices of a rectangle like this. If you didn't have this rectangle in mind, go ahead and sketch it. And what I would like to give you now as an exercise before I jump right into the proof computation is look at the difference in outputs and try to connect them to like geometric measurements for this rectangle. So we had 4 f values and some were being subtracted and some were being added. Can you relate them to any kind of geometric computation done on this rectangle? I'm going to name this sum and difference of 4 outputs for f n of hk. So imagine that we have fixed h and k. Here in my diagram, they are both positive, but it's like, don't slide them around. Don't take any kind of limit yet. Imagine that they are just fixed. So we're working with a non-zero h and k, and this quantity that we're going to work with, I'm calling it n for numerator because that's kind of where it lived in that iterated limit computation, and I'm going to treat it as a function of h and k. So later, if we slide h and k around, this will change as h and k change. Okay, what I've done here, I think this is how we had this expression when we first encountered it. Just factored out the negative to write these two a little bit differently, but it's still the same expression overall. And if you can see the color coding here, I'm saying that this difference is computing essentially the displacement along this lower rung, and this one is the upper rung. So here we're doing like 2 horizontal bar computations. That's what I was hoping for you to connect to a moment ago. Okay, I know you might be looking at these 2 expressions and saying, I know what to do. Those differ in the x coordinate only. We're going to pass to a rate of change because we just went through that warm-up exercise, but we're not actually going to do that quite yet. This is tricky. If you try to skip this step and go straight to a difference quotient expression with each of these pairs of terms individually, you don't really get to the right place. You get to something that's a little hard to work with. So actually, there's a step that we're going to introduce before we pass from differences in function outputs to derivatives. And that is, I'm going to actually invent out of thin air a new function. Let me call it w sub h b plus k minus w sub h of b. I have not told you what this is yet, so let me do so now. And just to be concise, I'm just going to do that right here, where w sub h is a function of just the second input y. So that's why I have the y values here. And we compute it by doing f of a plus h y minus f of a comma y. Okay, so let's pause for just a moment. These expressions right here are the same form as this and this. So that's why these two reduce down to w sub h of b plus k, because we have a plus h b plus k, and I get really turned around, a b plus k, right? And then the second two can be rewritten as wh of b. Let me give you a moment just to convince yourself that that's true. It's all written out here, but just take a moment to understand this step. It's tricky, and I'll explain why at the end it was necessary, why we couldn't work with these two expressions as they were given to us, and then hopefully it will be satisfying by the end. Okay, if you're like me, just carefully verified that this pairing looks like this, where y equals b plus k, and this pairing looks like this, where y equals b. Now we have a function of one variable, and we're looking at a function difference. So we can pass immediately to a rate of change. This is like the first example that we worked through in our warm-up slide. So let me just jump straight to WH prime, just plain old prime, because this is a function of one variable. Here, the action is happening in the y-coordinate, so I'm going to call this d sub 1 times k. So this is for some d1 between b and b plus k. Okay. We have now taken the derivative of w sub h. Let's take this and replace w sub h prime with the correct expressions in terms of f. What does it mean to do prime when we pass back to f? Well, notice here, the x-coordinates are fixed. They're not the same, but they're fixed. This is only a function of y, so we would never change these x-coordinates for f. So what we've done, wh prime, is differentiation just with respect to y. So we're going to replace wh prime with two partial derivatives for f with respect to y. So it's this derivative minus that derivative. Okay. Df dy at a plus h, that is fixed, but w prime at y means that this needs to be d1 minus df dy at a comma d1. So this is the same thing as w prime at d1 times k. Okay, now looking at this, we have two function outputs. The function in question is df dy, which differ with respect to just the x-coordinate. Take a moment to pause and see if you can pass from this to another layer of differentiation. So we want to replace this difference in outputs for f sub y with some sort of rate of change. This recalls the second and third examples from the warm-up example, notably the second example with capital H. The y-coordinate is fixed. The x-coordinates are varying. We're going to replace this with f sub y sub x. So differentiate this expression with respect to x. That derivative is being computed at some c1 between a and a plus h. So overall, it's going to be f sub yx at c1 d1. From this, we pick up h, and then we still have k. There's some c1 between a and a plus h. We're not done with the proof, but we're done with this part of it, which is taking that expression from our numerator when we did the iterated limits and viewing it as the difference between how f behaves on two horizontal bars The reason why the introduction of this capital W function was necessary, why we couldn't take this and say, hey, that looks like the warm-up activities, is because this expression, the way that we ordered these terms, so I preserved the ordering here, I just factored out a negative to get to the second line. This expression came from computing f sub xy. If we went right to using the warm-up activities on these two differences, we would pick up a derivative with respect to x, but we're trying to change the order. So instead of differentiating, passing to two partial derivatives with respect to x, we needed to reverse the order somehow, and that's exactly what this allowed us to do. So while this computation was designed for computing f sub xy, we were able to kind of force the order to switch and get down to something that looks like f sub yx. We are not at all done. For one thing, this is f sub yx at some point c1, d1, which actually I have now plotted in this rectangle. C1 is between A and A plus H, regardless of how these two are ordered. D1 is between B and B plus K, so we're somewhere in the interior of this rectangle. We are going to start over with this expression. So in a moment, I'm going to step aside, let you write this down. In a moment, I'm going to return to these four function outputs, but we're going to reverse the order. If you'd like to anticipate what the new ordering will be, notice that this computation came from looking at displacement along the horizontal bars. So that should be a clue to how to rearrange the expressions in this in expression to get to perhaps f sub xy. So geometrically, we've got to make a little change in how we were designing this computation relative to the rectangle. I'm not sure I said that clearly, but hopefully it will be clear when we resume in just a moment. Okay, you may have anticipated this algebraically or geometrically or maybe both. Before, we were working with this in expression, but we gave it some geometric meaning. We said we are evaluating along the horizontal bars. This time, we're going to switch to the vertical bars. And algebraically, the most natural way to do that is to take these terms and swap them. You can see it's still the same expression. I've just reversed the inner two terms. So now this expression looks like displacement along this right vertical bar, and this one is like this left vertical bar. We are going to just completely repeat all of the same ideas that we just did. So it's like exact same computation. We're just kind of reversing variables. So I would like for you to do each of the steps. Excuse me. I'll go drink some water while you write down the sort of weird, invented out of thin air function that we will need analogous to W sub H. That's the first place we're going to start. So see if you can come up with that. And then I will come back and write down that kind of trick function that feels like it comes out of nowhere. All right, once again, we're going to take this pairing and describe it as one function output where the function is a function of one variable, and it will be the same style for replacing these two terms. Hopefully, you were able to work out what this will look like. Let me call it capital L sub k, WH, like width, and written with respect to h, or the function dependent on h. Here, the definition of L depends on k. This is length. Normally, I would use h and height, but I feel like I've overused the letter h in this video, so let's just stick with this. Is going to be the name of the function. This one is going to be a plus h, and this one is going to be a. And if that's not what you came up with or you got stuck, let me give you another moment to now write down the definition of L sub k. It's a function of x, and what does it need to be? All right, this time, this is a function of x, and it's like this part is always the same, and then whatever we plug into L sub k goes here and here. So that will allow us to describe these two terms as this one function output, L sub k of a plus h. So a plus h will go here and here. And this pairing is L sub k of a. So it's a, b plus k, a, b. If you're wondering about my notation, I already explained capital W and capital L in terms of the sides of the rectangle. Sub k here means that, we fixed h and k back when we started this computation. So if I change k now, this is going to change. So it's like our function would update each time that we picked a new value of k. And the first one we looked at a few minutes ago, that would change as we changed h. So it's like once you fixed h and k, it makes sense to then define capital W and capital L. Okay, now we have a difference in function values, so a difference in outputs. See what you can make of this. Just like before, we're going to pass to a derivative. So L sub k prime at C2 times H, where C2 is between A and A plus H. So C, because this is happening in the X coordinate, and C2, because we've already got a C1, and it's not necessarily the same number. Okay, just like before, let's go ahead right now together and pass from LK prime to some sort of differential expression involving F. The y values here are completely fixed. This is in no way a function of y. The y values are b plus k and b. So differentiate L sub k means differentiate f with respect to x. So this is going to be f sub x at the point C2, b plus k, minus f sub x at C2, b. And then we have the h from before. Now we are looking at function outputs, which differ only in the y coordinate. So we're going to pass to a derivative with respect to y via sort of mean value theorem in the plane x equals C2. So just like before, we get to a mixed partial derivative, second order. This happens in the plane x equals C2, and now we're going to say, this is some kind of secant slope in that plane. We're passing to a tangent slope, which is happening when y equals D2. When we do that, we're picking up a k, just like we did in the warm-ups, and then we're carrying the h from before, where D2 is between b and b plus k. And I've added that to our rectangle as well. So for the same fixed h and k, sorry, I've got so many letters in this proof, that's why I'm kind of hesitating a few times. For the same fixed h and k, we can now take this expression and write it as equal to two different mixed partials. We had a moment ago f sub yx at C1 D1 times kh. Now we have f sub xy, different order, at C2 D2 times the same kh. So we know that at 2 points within this rectangle, it's the case that f sub yx at one of those points equals f sub xy at the other point. Now these points are different, but what we're going to do in just a moment is say, if we take the limit as h goes to 0 and k goes to 0, that's kind of like taking this top right corner and dragging it to the bottom left corner. So we're going to let the width and height of this rectangle shrink to 0. As we do that, you can imagine every time you drag that vertex down, you're picking a new h and k. You could repeat this. Your points C1, D1, C2, D2, they would move around. So for different rectangles, these interior points would shift. It's like as you take the limit, you imagine those points kind of traveling around in the rectangle, but ultimately they will be squeezed down to this lower left vertex. So it's like because these points, C1, D1, C2, D2, live in the interior of this rectangle, and we want to drive this rectangle down to just this point, this whole thing is going to get squeezed to happening at AB. So we will do in just a moment that f sub yx at AB is in fact equal to f sub xy at AB, and at that point we will be done with Clairaut's theorem. Once again, let me just mention that this kind of funny step here where we introduce this function is what allows us to reverse the order of differentiation in this problem. If you go back to that iterated limit computation and repeat what we did, but this time trying to compute f sub yx instead of f sub xy, you would end up with this kind of expression. So again, it's like if we want to do the reversal, this is how we bring in that reversal. All right, we are almost there. I just want to take that limiting idea that I kind of illustrated and just write it down. Okay, so let's summarize some of the observations we just made. As our sort of perturbation factors h and k go to 0, 0, C1, D1, that point goes to AB. C1 comma D1 goes to AB, and C2 D2 goes to AB. And that's essentially by the squeeze theorem. So C is between A and A plus H goes to A. D1 is between B and B plus K goes to B. So this point gets squeezed to AB, as does this point. Because the second partials are continuous, we also know what happens to f sub yx of C1 D1 and f sub xy of C2 D2. So by continuity, I believe it's yx that partners up with C1 D1. So f sub yx of C1 D1 goes to f sub yx of AB, and f sub xy of C2 D2 goes to f sub xy at AB. We're not quite done, but I just want to make these observations. In a moment, I'm going to start with this partial derivative, pass into a formal limit, and ultimately convert to this one. Before I do that, I want to mention that C1, D1, this point, and C2, D2, that point, they're functions of h and k. But the idea is for any choice of h and k, you take any pairing of h and k, there are points, C1, D1, and C2, D2, depending on those values, where the mixed partials are equal. So again, the mixed partials can be equal at different points inside this rectangle, but there are points where they are equal. So that's kind of the governing principle behind the limit that we just wrote down. I'm not going to spell out with notation that these are functions of h and k because there's already a little bit too much notation in this proof. So let me step aside. We'll just kind of erase these statements and I'll just write down the limit. It's very short at this point. All right, we're about 1 minute from the end of this. So f sub xy at the point AB is equal to the limit. What before was an iterated pair of limits is now just going to be a double limit. So I'm going to imagine taking this top right vertex and dragging it down in a two-dimensional way instead of in a one-dimensional and one-dimensional way. So it's one limiting action. So this pairing is going to 0, 0. And by the observation we just made with continuity, this is going to be the limit of f sub xy at C2, D2, where it's like for each hk you pick, that's how you choose these points. And for each hk you pick, once you've chosen these points, there's a way for you to now switch the order. So for any choice of h and k, we can take this and replace it. It's equality to replace it with f sub yx at C1, D1. But now by continuity, this is no more limit. F sub yx at AB, and now we prove Clairaut's theorem.